Okay, before I proceed, are there any questions with respect to Module 1 that you'd like clarified? Because we're starting a new module today, that's Module 2. Any questions with respect to Module 1 that you want clarified? Okay, if you have any questions anyway, there's still UVLE, no? Rather, there's still a Piazza where you can post your questions. Okay, so today we start a new topic. This is Module 2, where we discuss the basic semiconductor devices. Module 2 will also include a discussion on op-amps, something beyond what you learned about op-amps in EEE 1, 2, 3. Just a while, there's a question. Yes, no? Any question? Sino to? Neo? Okay. Sorry, there's a question from one of your classmates. Kailan mag-umpisa yung face-to-face classes? Right now, nag-i-install pa ng equipment dun sa kwarto na dapat gagamitin. Sabi nila, they're going to finish installation within the week, and then I'm going to inspect it late in the week or next week. If it seems that the facility is ready, then we might have face-to-face classes the week after next. So it more or less ganun yung scheduling. Okay. Okay, so like I said, we're going to start Module 2 today. Module 2 is a discussion of basic semiconductor devices, and also includes a discussion of operational amplifiers beyond what was taught to you in EEE 1, 2, 3. Okay. I am the handler in charge of Module 2, so all of the material that is published in UVLE, including the recorded videos that came from me. I'm not going to repeat my videos. I'm not going to repeat my lectures, rather. You can listen to the recordings that I posted in UVLE. I'm just going to touch on the more important parts, the parts that I think I should emphasize upon in the lectures that I published. It's important that you take a look at this first before attending the synchronous sessions. Otherwise, you might not be able to catch up with the material that I'm going to be presenting. Okay. Again, I reiterate, if you have any questions, I don't see the chat box. I might not notice something new in the chat box. Just shout it out, no? If you have any questions, and I'll stop and I'll explain further if you have something to be clarified. So let me go to what I wanted to cover for today. Okay, so there was a part 1. So the diode section of Module 2 is broken up into 3 subparts. Okay, the part 1 is really just a review of EEE 1, 2, 3, where you took up the piecewise linear models of your diode. I did not publish a video recording of that lecture because this is just supposed to be a review. And I'm also not going to touch upon it anymore. Just go through it. It's echoing of what you studied before. No? So I'm going to start with the second part for diodes, which is the exponential and small signal models of the diode. So you took this up. This was already introduced to you in Module 1 when you took up the PN junction. This is the exponential model of the diode, and this is based on Shockley's equation. Where we have this reference directions. So this is I sub D, the current through your diode, and this is V sub D, the voltage across your diode. In 1, 2, 3, you learned that this is the anode terminal and this is the cathode terminal. So the reference direction for the voltage across your diode is always anode positive with respect to the cathode. And the direction of current flow, the reference direction of current flow, is always along the direction of the diode, arrow. Okay, so you already know Shockley's equation. I sub S is your reverse saturation current. V sub T is the thermal voltage, which at 300 degrees Kelvin or 27 degrees centigrade is equal to 26 millivolts. Eta is your ideality factor. No? Yeah. So eta is your ideality factor. And this is usually equal to 1 for well-fabricated diodes. And the diodes that we use are usually well-fabricated. So you're going to see oftentimes that this eta is actually omitted in the equation. Okay. Now for normal values of V sub D, okay, so first of all, no, if V sub D is greater than 0, then we say that your diode is forward biased. Okay. And for normal values, for normal forward biased voltages, you're going to notice that E to the V sub D over eta V sub T will be very much greater than 1. Just to give an example, okay? Let's let V sub D equal to 0.3. Now 0.3 is actually less than the cut-in voltage, no? Less than the silicon cut-in voltage. What is the cut-in voltage for silicon? Can somebody shout it out to me?
Is that 0.7?
Yeah, that's right. Ano? That is the cut-in voltage if we're using the piecewise linear model. So, yung linear models natin, we have 3. Okay, just a quick review. We have 3 piecewise linear models. You have your ideal model, you have your constant voltage source model, and then you have your constant voltage source with forward resistance model. Those are the 3 models, no? So ito hindi na ito linear, no? This is no longer a linear model. This is now your exponential model. So itong 0.3 is even less than yung 0.7. So we remember that when the voltage is less than the cut-in voltage, we expect our current to be very small. Now let's compute for E to the V sub D over eta V sub T. No? If I compute for E to the 0.3 over 1 multiplied by 0.026, you just try to compute for that. The value, and I have it here, is 102,000. Yeah, 102,386. Okay. So if you take a look at this, this is obviously very much greater than 1. Itong value to, under normal circumstances, will be very much greater than 1. No? And therefore, a lot of times, you just see the equation I sub D is equal to I sub S, E to the V sub D over NVT. Dinidisregard na yung 1. Okay, on the other hand, when V sub D is less than 0, so this is now reverse biased, okay, for normal reverse bias voltages, itong E of V sub D over NVT will be approximately equal to 0. Kasi ito negative, no? Itong value to, V sub D will be negative. Okay, so E to a negative number, so that's 1 over E to that number, so it's obviously a number less than 1. And as the denominator gets bigger, that number approaches 0. Right? That's why this becomes approximately equal to 0 when V sub D is negative. When V sub D is negative. So what happens? You get I sub D is equal to negative I sub S. Kasi kung ito 0, ang matitira na lang is negative 1. I sub D is equal to minus I sub S. So this is a very small number. No? We said that I sub S, this is your reverse saturation current. This is anywhere from 10 to the minus 9 to 10 to the minus 15. So it's from the nanoampere range to the femtoampere range. And that's why for all practical purposes, when your diode is reverse biased, we can approximate the current to be equal to 0. Because I sub S is a very, very small number. Okay, I just want you to be familiar with this formula. No? So I want you to do this on your own now. No? You get out your calculators, your pencils, or your ball pens and your paper, and I just want you to solve this. No? Let's say a diode has I sub S equal to 10 to the minus 14, an ideality factor of 1 at 27 degrees centigrade. What is the voltage across the diode if the current through the diode is 10 MA? So these are in the notes. The answer is in the notes. Please don't look at the notes. I just want you to try solving this problem. I'll give you about 5 minutes. You should be able to solve this in 1-2 minutes. If you have an answer, please post it. Please put it in the chat box so that I see more or less how many people have already been able to come up with an answer. Then we'll discuss it after. So please try. No? Wag sana yung ano lang, no? Manonood na lang kayo kung sa ibang gumagawa, no? Please try. Okay, I have 2 answers already, 3. So far, so good. Yes, no, I have answers from Rondell, from Nico, from Dean Kyle, John, and Ross, and so far all the answers are correct. No? So maybe we can stop there. Okay, so for the sake of those that were not able to come up with an answer, so let's just go through this very quickly. Okay, so the fact that you have 10 MA flowing through the diode means that there's already a substantial voltage that is across it, at least somewhere in the vicinity of the cut-in voltage. And therefore, we can now use the formula I sub D is equal to I sub S e to the VD over eta VT, because the 1 will be insignificant. Okay, if I wanted to solve for V sub D, okay, V sub D will just now be equal to eta V sub T ln of I sub D over I sub S. So it's just now a matter of substitution. Your eta is equal to 1, V sub D is 0.026, and then you have the ln of your current is 10 MA. Okay, so this is 10 times 10 to the minus 3 or 10 to the minus 2. And then I sub S is 10 to the minus 14. And if you compute for this, you're going to get 0.026 72 volts. Actually 0.718. So seems that everybody got it. Wala namang problema. 0.718. Okay. Yeah. Letter B. What if it is 50 MA? That's supposed to be the second part of this problem. What if it is 50 MA? So I don't think you need to go through this exercise anymore. It's just direct substitution. If 50 MA, I'm going to get V sub D is equal to 0.76 volts. Okay. Take note that my current was multiplied by 5, but my voltage only changed by 0.04 volts. So the takeaway from this is my current increased 5-fold, but the voltage changed by only 0.04 volts. And that's typical of the diode. No? You remember that we said that in the forward region for silicon, the diode voltage is approximately 0.7 volts. No? So yeah, we're somewhere there, no? 0.72 and 0.76. So we're actually in the, okay, we're actually somewhere here. Right? Your voltage is, okay, between 0.72 and 0.76, but your current increased drastically, no? From 10 MA to 50 MA. So this is now your I sub D versus your V sub D. Are there any questions? Okay. Here's a little bit more difficult problem. The circuit shown employs two identical silicon diodes. Assume the temperature is 27 degrees centigrade. Use the exponential model to determine the voltage across each diode if the ideality factor is 1. So how do we solve this problem? Okay. My question to you is this. If these two diodes were ideal, notice that they are back-to-back opposing. The two diodes are ideal. What is going to be the value of I sub D? Assuming that the two diodes are ideal. Can somebody shout out an answer?
0 po, sir.
Ano yun? I didn't hear.
0 po.
0?
Opo, sir.
Yeah. Bakit 0?
Kasi
Tama
po,
yung sagot, ano? Bakit 0?
yung dito po, cut off siya, sir. Kaya no current po.
That's right, no? Kasi these are connected in series opposing. So remember, if it's an ideal diode can only support current flow in one direction. Your current, dahil dito sa 5-volt source, your current is trying to flow in the clockwise direction because of the 5-volt source. So D1 can support the flow of current. But D2 cannot support the flow of current. No? Kumukontra siya dito sa direction ng diode. And therefore, if the diodes were ideal, I sub D will be equal to 0. Okay, now, supposing these are silicon diodes, and these diodes are not ideal, what do you expect the value of I sub D to be? Can I hear from somebody else? Ano yung magiging value ng I sub D kung hindi ideal tong mga diodes na to? Anyone? Anyone want to make a brave guess?
Equal po siya sa reverse saturation current.
That's right, no? It will be equal to the reverse saturation current. No? So I sub D in this case will be equal to I sub S. Okay, why? No? Well, if I sub D is trying to flow in the clockwise direction, okay, that means this diode is forward biased. No? if this diode is forward biased, that means the voltage across it will be small, especially since I sub D is small. No? Kung maliit na maliit yung I sub D, maliit na maliit din tong V1. And therefore, itong V2, magiging malaki. No? Kasi kung maliit yung V1, malaki yung V2. But note that V2 is reverse biasing D2. And we said that when we are reverse biasing a diode and the bias is a substantial voltage, then ID is equal to minus I of S. ID is equal to minus I of S. Bakit dito positive? Why is it positive I of S? Well, because the direction of flow of ID is opposite the reference direction for D2. Yung reference direction of current for D2 dapat paakyat, itong ID pababa, and therefore nagiging positive yung I of S. Any questions with regard to that? Kung bakit positive yung I of S? No, it's because of remember our reference direction is usually current flowing from anode to cathode. Okay, so I of D is equal to I of S. If you take a look for D1, I have the equation I of D is equal to I of S, okay, e to the V1 is my voltage across D1, eta is equal to 1, no? So this is just over V of T minus 1. I cannot assume that this one is negligible because most likely itong value ng V1 will be very small because my I of D will be very small, no? So this is going to be very small, so I cannot assume that this one is negligible. Okay, but what I was able to conclude was this is equal to I of S. I of D is equal to I of S. So what does that mean? It means that e to the V1 over V of T minus 1 is equal to 1. Is equal to 1. Dahil magka-cancel out ng dalawang I of S na to. Or e to the V1 over V of T is equal to 2. But what is V of T? V of T is 0.026, no? Because we're operating at 300 degrees Kelvin. So we can compute now for V1 that is equal to 0.026 ln of 2. Okay. And if you compute that, okay, I have it somewhere here. No, let me just check my notes. Yeah, if you compute that, I'm going to get V1 is equal to 0.018 volts or 18 millivolts. 18 millivolts. So very small, very, very small, which is consistent with what we know about silicon diodes, for example, that when the voltage is less than 0.7, your current is practically equal to 0. Okay. So having said that, what is the value of V2? What is now the value of V2? Anyone? Should be easy now for you to determine V2.
Sir,
Yes,
4.982 volts po.
that's right. And that's just KVL, no? So from KVL, V2 is 4.928 volts. Okay. Because V1 plus V2 must be equal to 5 volts.
Sir,
Yes.
4.982 volts po
Ah,
yata, sir.
Yeah, you're right. Sorry. Thank you. $4.982. Thank you. Okay. So, by the way, Shockley's equation is an idealized equation. No? It assumes that the diode is behaving as its physics model says it should behave. No? Of course, there are plenty of factors that will cause a diode not to behave as its physics model. No? The manufacturing processes, the doping levels, for example, there are many factors that can come into play. But if we assume that the diode behaves as its Shockley model dictates it should, then these are the voltages that will appear across my diodes: 0.018 volt and 4.982 volts. Okay. Note that these voltages are actually independent of the reverse saturation current, because our reverse saturation current got canceled out. Okay, so that's the exponential model of the diode. Okay, the next topic is we're going to take up the small signal model of the diode. But before we take up the small signal model, I think it is important that we differentiate small signal analysis from large signal analysis. You're going to get into this material again when we take up amplifiers. What is small signal and what is large signal? So this is really just an introduction. Let me differentiate the two. When we say large signal model, that is the model that is used over a large range of voltage or current. When your voltage or current changes with big amplitudes, then we use the large signal model. But when your voltage or current is restricted to small variations, ibig sabihin yung pagbabago sa voltage or sa current maliit na maliit lang, then we can use a small signal model. Now, for semiconductor devices, your model is usually either exponential or polynomial. The diode I already showed you has an exponential model. That is your Shockley model. That's your exponential model. When you go to the bipolar junction transistor, we're going to take that up shortly, you're going to see that it also has an exponential model. When you go to the MOSFET, and you learn this from EEE 123, what is in saturation, I of D is equal to K VGS minus VTH quantity squared. That's polynomial. So typically your devices are either exponential or polynomial. Now, these equations are nonlinear, and it's very hard to solve nonlinear equations. If, for example, in this particular exercise, if we did not disregard the 1, kasi yung Shockley equation, I of D is equal to I of S e to the VD NVT minus 1. Kung hindi natin tinanggal yung 1, I won't be able to come up with this expression. I won't be able to come up with a closed expression of V of D in terms of I of D. And that's the nature of nonlinear equations. So with the large signal model, it's difficult to perform circuit analysis because your equations are nonlinear. On the other hand, in the small signal model, because the signals are varying very small variations, your device can be considered linear over the signal range. If it's considered linear, you can replace your device with linear elements. Your linear elements are either your resistor, your inductor, or your capacitor. And when you have circuits consisting of RLC, you already know how to solve those circuits. You solve those circuits already in EEE 123. Gagamitan mo lang ng yung mga natutunan nyo, nodal analysis, later on you learn mesh analysis, you can use network simplification, you can use Thevenin's theorem, and so forth. You can use all of that. Basta linear yung elements mo. No? Hindi mo pwedeng gamitin yon pag exponential yung elements mo or pag polynomial yung elements mo. Okay? So your tools available for linear circuit analysis can be applied. Anyway, so we have different uses for the two types of analysis. Large signal model, we use that in determining the DC operating point. We can use that to determine the transfer characteristics, which we're going to do later on. And you can use that for low frequency analysis using point-by-point calculation. On the other hand, your small signal model, that's how we usually determine the characteristics of amplifiers. That's how we determine the gain, the input and output impedance, and even the frequency response. So that is the difference between large signal and small signal analysis. Are there any questions?
Sir,
Yes, sir.
is there a range to differentiate if a signal is large or small?
That's a good question. No? It actually depends on the device. Because the key there is as the signal varies, your device parameter should not vary within the variation of the signal. No? That's what will make it linear. For example, no? If you're talking about a resistor within the range of voltages, your resistor value should not change. No? If you're talking about a resistor, so it depends on the component, no? But more or less, just rule of thumb lang, no? In the devices that we deal with, it's usually in the millivolt range. Usually in the millivolt range. Okay, I hope that answered your question. Any other questions? Okay, so how do we determine then the circuit response? Now, in electronic systems, signals often consist of two components. You have a DC component and you have a time-varying component. So in the future, when you study your amplifiers, for example, you're going to see that the signals that exist in your circuit will usually consist of a DC component plus a time-varying component. So let me give an example. So this is my signal. So I'm showing you here that my signal is not constant with time. It varies with time. And in fact, in my example, it varies sinusoidally with time. But notice that this sinusoidal signal, okay, has been translated upward. Your normal sinusoid would have been here. But in this particular case, it was translated upward. In other words, itong level na to, I call this the DC component of my signal. And then this variation, I call that the time-varying component of my signal. So if my signal is small v capital IN, that consists of capital V capital IN, which is my DC component, plus small v small in, which is my time-varying component. A lot of books will call it the AC component. I prefer to call it the time-varying component. So these are the types of signals that we often encounter in electronics. So how do we determine the circuit response? We use the principle of superposition. You learned the principle of superposition in 1, 2, 3. If you have multiple sources, we learned in 1, 2, 3, and your circuit is a linear circuit, then the total response is due to the algebraic sum of the response of the circuit with the different sources acting alone. Okay, so we can take a look. If this is my source, we can take a look at this as having two components, a DC component and a time-varying component, and my total response will be the response to the DC component plus the response to my time-varying component. That is using the principle of superposition. Okay, I want to discuss, before proceeding, I just want to discuss conventions on notation. So notice my variable can be lowercase, it can be uppercase, my subscript can also be lowercase, and my subscript can also be uppercase. So my variable, I have lowercase and I have uppercase. And then the subscript, I also have lowercase and uppercase. I don't know if this was impressed upon you in EEE 123, but what does it mean when my variable is lowercase? Does anybody here remember? What does it mean what does it usually mean when my variable is lowercase? Anyone?
Sir,
Yes?
time dependent po siya.
Yes, that's right, no? When my variable is lowercase, that means that the value of my variable changes with time. On the other hand, when my variable is uppercase, ang ibig sabihin nun, it is DC basically, no? It does not change with time. My variable does not change with time. Now we add a complication here, no? Because we have a subscript, and the subscript can be lowercase and can also be uppercase, no? For example, if I have V in, no? The V, lowercase in V in, indicates that V in is time varying, no? But the in, uppercase, okay, uppercase in V in indicates that this is the total signal. So if I have a lowercase variable with uppercase subscripts, that means that that is a total signal. Such as this, it's a total signal. If I have lowercase subscripts in a lowercase variable, so lowercase subscript in a lowercase variable, that means that V in here, small v, small in, is the time varying component of small v, capital In. So this is the time varying component of this. On the other hand, capital V with uppercase subscripts means that this is the DC component of Vn. Okay, so don't take the case for granted. No? Importante yung case. So this is the convention that was adopted by Zener and Smith in the microelectronics book, no? Microelectronic circuits book, which is our main reference for this course. Importante yung subscript. The subscript gives you an idea of the nature of that particular variable. Are there any questions with regard to that? So for example, pag sinabi kong I in, anong ibig sabihin nito? I small in. Anong ibig sabihin yan?
Time varying current po.
Yeah, first of all, it's a time varying current. But what does this small in mean? No, this is the time varying component of I in. Remember, this is going to be my total signal, and that means this is the time varying component of this total signal. Okay, are there any questions? Okay, so going back to the problem, large signal versus small signal analysis. So here is a diode, and I'm going to excite the diode. In other words, I'm going to connect a source to the diode, but actually this source consists of two components. I have a DC component and I have a time varying component. Okay. So the sum of these two voltages, I'm going to apply to my diode. I'm going to get a current that will flow, I sub D. Okay, now V sub D will be equal to the sum of my DC component and my time varying component, no? Kasi itong V sub D is just equal to this plus this. The response, I sub D, will also have a DC component and a time varying component. My excitation has a DC and a time varying. My response will also have a DC and a time varying. Now, how do we visualize that? Okay, if I draw the diode characteristic curve, okay, so let's assume that this is my diode characteristic curve. So this is a plot of I of D versus V of D. Okay, so notice that my subscript is uppercase, meaning to say this is the total signal. No? This is the total diode current, and this is the total diode voltage. So what will my diode characteristic curve look like? Okay, let me use a different color. So let's say this is my diode characteristic curve. Okay, let's say that is my diode characteristic curve. So more or less, this will follow the exponential model or the Shockley model of the diode. Okay, this V sub D establishes this I sub D. In other words, if I apply a voltage V sub D, I apply this voltage V sub D, I expect to get the current I sub D. And this is what I call my DC operating point. This is now what you call the DC operating point. Okay, what will this V sub D do? If I add this to this, okay, that is going to make this point go up and down. So habang nag-oscillate tong small d, habang gumagalaw to, gagalaw tong point na to, no? So that will follow, for example, let's use a different color. That will follow this path, no? That might follow this path. We're now here. Okay. This is actually now my value of V sub D. If we take a look at it versus time. So as my V sub D oscillates, as small V sub D oscillates, this point here goes up and down. And what happens to my current? This is what will happen to my current now. It is also going to go up and down. And this is now going to be my I sub D. Okay. So do you get what's happening from this point on? It will be going up the curve and down the curve, up the curve, down the curve, because of this V sub D, and it's going to result in a current going up and down also. Okay. So that is how the principle of superposition is applied. No? So itong capital I, capital D is determined from capital D, usually using large signal analysis, because the value of I sub D is large, no? And the resulting value of V sub D is also relatively large. The small I, small d is determined from the small v, small d using small signal analysis. Okay, if the amplitude of V sub D is small, So if this is small, so it's redrawn here, no? Itong maliit na maliit, itong V sub D, and earlier there's a question, what is small? Well, usually in the range of millivolts, it's small. But what is important is this, no? It should be small enough so that this is approximately equal to a straight line. So if I blow this up, what I want actually is to be able to approximate the black curve here with the blue curve. I want to approximate the black curve with the blue curve. If the blue curve no longer approximates the black curve, then you can no longer use small signal analysis. So that's what I was trying to explain earlier. It depends on the device. Okay. Now the slope of this blue curve is going to be 1 over R sub D. The slope of this blue curve is going to have the unit conductance. No? So if you get the reciprocal of conductance, that is resistance. That's going to be 1 over R sub D. So you try to get the slope of the curve with respect to this point, and that is 1 over R sub D. And what we're saying now is, from the point of view of small v, small d, you can now represent the diode by a resistor whose value is small r, small d. The diode can be replaced by a resistor. What is the value of this resistance going to be? You can compute the value of that resistance using Shockley's equation. I have I sub d. I have I sub d is equal to I sub s e to the v sub d over nvt minus 1. If I get the partial of I sub d with respect to v, that is equal to g sub d. That is a conductance. So that's what I'm showing here. G sub d is the partial of I sub d with respect to v sub d. So that's the partial of this with respect to v sub d. So I'm just getting the derivative of this expression with respect to v. Now I can disregard the 1 because the voltages that I will be applying are going to be substantial, so I can disregard the 1. So I'm really just getting the derivative of this. And if I get the derivative of this is what I come up with. Okay. If I simplify this term here, I sub s e to the v sub d over n v sub t, this is actually equal to I sub d. That's why I end up with this. That's why I end up with this. And this I sub d, itong value ng I sub d na to, should be computed at this particular point. So this I sub d will depend on this particular voltage, this particular voltage. If I now want to get the resistance, all I have to do is get the reciprocal of this. So ito yung lalabas. Again, it is a function of I sub d. It's a function of this. No? In other words, if I try to compute for r at this point, I'll come up with a different value because I have a different slope. Here I have a different slope. So here I come up with a different value. Okay, do not confuse this with the piecewise linear model of the diode, where the diode is a constant voltage source with forward resistance. This is different. This is your small signal model. Dun sa piecewise linear model, you have a constant voltage source with forward resistance. That the slope of that is that model looks something like this. Excuse me. That model looks something like this. where this is V's of F. And then this is 1 over R's of D. So it might be close. Itong small R's of D might be close to this, but it is not exactly the same. So ito yung isang model ng diode na kinuha natin sa EEE 123, no? Which we also reviewed in part 1. Are there any questions? Okay, so let's take an example. So here's a problem. The diode is silicon with ideality equal to 1, reverse saturation current of 10 to the minus 15. Please excuse me for a while. No? I have a call coming in. Yeah, sorry about that. No? So yeah, in this example, the diode is silicon with ideality equal to 1, reverse saturation current 10 to the minus 15, operating at 27 degrees centigrade. So I have a circuit where I have a capacitor in parallel with the diode, a resistor that is in series with the diode capacitor parallel combination. And then I have an excitation which consists of a DC source in series with an AC source. Okay, so if this is my excitation, expect that my response, I sub x, will also have a DC component and an AC component. So what I want to do here is to determine a time domain expression for my I sub x. This is the total response, which will have a DC component and a time domain component. Okay, so we said we can split this problem into two. We use the principle of superposition. First, we make V of x act alone. We make V of x act alone, and we determine capital I, capital X. And then we make itong small v of x act alone, and we determine small I, small x. And then we add the two, and then we get the total response. So let's determine first capital I, capital X. If v of x is acting alone, what do I do with this? Can somebody shout it out to me? Anong gagawin ko dito sa small v, small x?
Is short po, sir.
Yes, that's right. No. principle of superposition, you suppress the other voltage sources, so you replace this with a short. Okay. Second question. If my circuit is DC, no? So kung ito lang yung source ko, my circuit is DC, what is the equivalent of this capacitor at steady state? Can I hear from someone else?
Sir, open circuit.
That's right. It's going to be an open circuit, no? Because your capacitor for DC excitation at steady state is an open circuit. So if I short this and I consider this an open circuit, ito na lang yung matitira. Okay. This is all that's left. So this is now how I can compute for capital I, capital X. If I were to use the piecewise linear model of the diode, and the diode was silicon, anong value nitong I sub X? Using the piecewise linear model and assuming the diode is silicon, can somebody tell me what the value of this I sub X is going to be? Anyone? You should be able to, if you have your calculator, you should be able to key that in just a few seconds.
Two milliamps.
That's right, 2 milliamps. No. So how did you get that? Can you explain to your classmates?
If we're assuming that the diode is in forward active, we know that it has a voltage drop of 0.7 volts.
That's
And
right.
since the Vx is 0.8, it means the voltage drop across the resistor is 0.1 volts. So the current Ix across the resistor would be 0.1 volts over 50 ohms, which is 2 milliamps.
Okay, so yeah, that very good, no? So that's right, no? So if we were using the piecewise linear model of the diode, your I sub X will be equal to 2 mi, no? Using piecewise linear model, assuming P sub D is equal to 0.7. But actually, we can do a more accurate calculation. Because in this particular problem, you're given all of this data. No? You're given eta, you're given I sub S, you're given your operating temperature. You should be able to use Shockley's equation. So let's just use Shockley's equation. Later on, let's compare this to the 2 milliamp. So assuming that it's an idealized diode, not an ideal diode, no, an idealized diode. So using Shockley's equation, okay, I have I sub X, no, is equal to I sub S e to the B sub D, B capital D, over N B sub T minus 1. Okay, so I'm just yeah, this I sub X is the current through the diode, no, using this particular circuit. This capital V capital D is the voltage across the diode in this circuit. Okay, and then V sub T is my thermal voltage. So if I substitute, I have 10 to the minus 15 e to the V sub D. Eta is equal to 1. V sub T is 0.026 minus 1. So this is my first equation. What is my second equation? My second equation is just KVL. Right? I sub X, exactly as what was mentioned by your classmate just now. I sub X is equal to V sub X minus V sub D over 50 ohms. which is equal to 0.8 minus V sub D over 50. So this is equation 2. Okay. So I can, from here, I can solve for V sub D. Okay, what is V sub D? V sub D is equal to 0.8 minus 50 I sub x. And then I can substitute that V sub D up here. So I'm going to get I sub x is equal to 10 to the minus 15 e to the 0.8 minus 50 I sub x over 0.026 minus 1. One equation, one unknown. Now, how do you solve this equation? Anyone? How do you solve for I sub x? Anyone? If I were to give you this equation, or if you encounter this equation in your exam, how would you solve it? No one would be able to solve this. You have no idea?
Sir, try lang po.
Huh?
Try lang po. What I'll try po siguro is to convert yung E to ln first.
No. Actually, kasi this has no closed form solution. That's what I'm trying to say, and that's why solving nonlinear equations is very difficult, because it has no closed form solution. But you actually have a tool that can solve this, and what is that? Your calculator.
The shift solve po.
Yes, exactly. No, yung solve function ng calculator no can solve this. Nung estudyante kami, the only way we could solve this was we would have to do trial and error. No, but you can use your solve function. Okay, so that's how I would tell you to do it. No? Just use the solve function of your calculator. Ngayon, kung wala kayong calculator na may solve function, then you'd have to use trial and error. Okay, so using the solve function, I'm going to get I sub x is equal to, and I have it somewhere. No? Sorry, let me check my notes. No. Yeah, I'm going to get I sub x is equal to 1.44 MA. So medyo hindi malapit sa dito sa to MA. No, it's about 1.44 MA. Okay, are there any questions? So this is how you would solve it if you were told to use Shakti's model. Okay, now depending on how well the parameters of your model are defined, like I sub s, your ideality factor, and your how precise your thermal voltage is, then this should come up with a more accurate determination of I sub x than using the piecewise linear model. But actually, in many instances, using the piecewise linear model is sufficient enough to come up with a good approximation. Are there any questions?
Sir.
Yes,
Sir, kung ganyan po, halimbawa po, diba, 2 MA yung nakuha doon sa piecewise linear, and then dito po sa Shockley, 1.44. Any naman po ay tatanggapin po, sir.
Sasabihin naman sa inyo yun, what model is acceptable to use. No?
Oh, so bali sir, sa exam po, ilalagay din sa tanong po.
Well, it depends kasi kung ano yung given. Kasi obviously dito, from the given, they're already telling you the parameters of the Shockley model. No? Pero pag hindi given yung I sub s, no? Pag hindi given yung operating temperature, wala kang choice. The only thing you have going for you is the piecewise linear model.
Noted po, sir. Thank you po.
Okay. So anyway, so kalahati ng problem na solve na natin, ano? Remember we said that itong ice of x will have two components. It will have a DC component and a time varying component. So nakuha na natin tong DC component. So ang kulang na lang itong time varying component. So para makuha natin to, ito naman ngayon yung acting alone natin. No? This is what we do acting alone, and therefore this is what we replace with a short circuit. Now, what we're saying is if this is small signal, this diode we can represent with a resistance. That is what we're saying here. The diode can be represented by a resistance. And if we represent this by a resistance, this is what we end up having. Okay, this is what we end up having. Now here we have V of x. We said that V of x, this is a 5 volt RMS, 1 kilohertz signal. And you're supposed to compute for I of x. Now, where did you learn to solve this? You learned this in 1, 2, 3. No? How do you solve this in 1, 2, 3? Do you remember how? What method do you use? Anyone? I have an AC signal at a given frequency, and then I have a linear circuit. How do I get the steady state response?
Sir, phasor po.
Exactly. So that's what I was saying now, no? Because this is now a resistor, you can use your linear circuit techniques. And the phasor method is a linear circuit technique. So with your variation in I of x, in V of x, you can now get the corresponding variation in I of x. So you can use the phasor method. Okay. First, I have to determine R of D. R of D is equal to I of D over NVT, remember? And then we already determined I of D is equal to I of X. No? Because this is the operating point of the diode, the DC operating point. But we already determined that to be I of X earlier. So this is NVT. So this is 1.44 divided by 1 divided by 0.026. No? And I'm going to get, sorry, let me clean this up. And I'm going to get, 18.06 ohms. Oh, no, sorry, this is G sub D, no? Excuse me, no? This is baliktad, no? This is G sub D. Ito yung R sub D is the reciprocal, no? 1 over R sub D to, no? So 1 over R sub D is this. So R sub D, if I compute for R sub D, I'm going to get 18.06 ohms. Sorry for that. Okay. And then if I look into this circuit, I have a Z equivalent here, right? Z equivalent is equal to R plus RD in parallel with Z of C, no? Where Z of C is equal to minus J over omega C. Okay, that's minus J over omega is equal to 2 pi times F. So that's 2 pi times 1000. And then C is 10 microfarads. So 10 times 10 to the minus 6. Anyway, if I compute for Z's of C, this is equal to minus J, 15.92 ohms. So my phasor current is equal to my phasor voltage, V of X, divided by R, value ng R is 50, plus 18.06 in parallel with J, with minus J, 15.92. Anyway, this is really just what you learned in 1, 2, 3. So I don't have time to go into more detail. This is what you learned in 1, 2, 3. So yeah, I'm repeating the expression for phasor I of X here. So this is my phasor voltage. This is my equivalent impedance. I'm going to get this I of X. So this is in phasor form. If I convert this now to time domain form, remember this is RMS. So this is RMS, and this is peak. No? So Vp is equal to the square root of 2V RMS. You remember that formula. So if you multiply this by square root of 2, you're going to get this, and this is now going to be your time domain expression. And finally, using superposition, this is just your DC component plus your AC component, so you're going to get this. So that's just a little bit of review of your phasor method. And you were able to get this because you modeled your diode as a resistor. And you modeled the diode as a resistor because you assume that when your input is only changing by 5 millivolts, then you're operating in practically a straight line in your diode characteristic curve. Okay. Any questions with respect to that? Okay, there's one more thing I wanted to share with you this morning. I'm sorry, I'm running a bit out of time here, but just give me 5 minutes. I just wanted to share with you some information on Zener diodes. Okay, so the last subtopic under diodes is other diode types. The last part of that is just a very qualitative description of some diode types. Just read through that, and there's also a short video which will describe those other diodes in more detail. What I wanted to explain a bit further is the type of diode which we call the Zener diode, because this is something that you're going to encounter quite often in electronics. So you recall that this is your diode characteristic. These are your diode characteristics. Okay, you have your reverse region and you have your forward region. What will happen if you continue to increase the reverse bias across a diode? There comes a time when all of a sudden we say the diode breaks down. All of a sudden, the current will rise. Will rise in the negative direction very steeply at that point where the diode breaks down. And there's a reason for that in physics. One of the reasons is because of the very strong electric field. You have a reverse voltage, so you have a very strong electric field. Your covalent bonds just rupture, and then you have electron-hole pairs that are released. So that's one of the reasons. The other reason is because of your very high band bending, the electrons due to drift gain a lot of kinetic energy, collide with other electrons, other covalent electrons, knock them off. Those in turn knock off additional electrons, and there's what is called an avalanche effect. That's what you call avalanche multiplication. So those are two mechanisms for breakdown. The important thing is this, that at some point, your current will steeply increase in the negative direction. And that happens at a voltage which we call the Zener voltage, V sub Z. And this is what we call Zener breakdown. So your Zener diode is designed to operate in the breakdown region. In the breakdown region, this curve is much steeper than this curve. This curve is still exponential in nature, whereas this is practically vertical in the breakdown region. And that makes the diode good to use as a voltage regulator here. Because if you put this diode across a load, you can maintain the voltage across the load at V sub Z, provided, of course, that the input voltage satisfies a certain criteria. So you use it as a voltage regulator, and we have a special symbol for that, and this is the symbol. So there are going to be three operating modes for the Zener diode. First of all, you have the conducting mode, and that is when your voltage is approximately okay. How do you know that your diode is in conducting mode? Well, you take out the diode from the circuit and you measure the open circuit voltage across its terminals. So you remember, this is one of the ways of determining the state of the diode. You take the diode out, you measure the open circuit voltage across its terminals. If that open circuit voltage is greater than V sub F, then you know it's conducting. And your diode is just equivalent to a constant voltage source. So this is the second approximation of the diode, the second piecewise linear approximation of the diode, the constant voltage source. Okay, when the open circuit voltage is between V sub F and negative V sub Z, your current is practically zero. Your diode is equivalent to an open circuit. On the other hand, if your open circuit voltage is greater than V sub Z, your voltage will be clipped at V sub Z. So you're now going to have a voltage source, constant voltage source at V sub Z. And notice that this is going to be opposite in polarity now. In other words, this is going to be the direction of your diode, and this is going to be the polarity of your voltage source. Nagbaliktad, ano? So this is in forward mode, and this is in Zener mode. Now, usually when you have a Zener diode, we reverse the direction of current, we reverse the reference direction of current and the reference polarity of the voltage. So just a very simple example is given. So the Zener diode is silicon with a breakdown voltage of 5 volts. Draw the output waveform of the circuit in response to the given input. So let's just do that very quickly. So when will the Zener be in breakdown mode? So again, notice that I already reversed the reference voltage polarity of the Zener. And your reference direction of current is actually going to be clockwise now. It's going to be clockwise. So it's opposite the direction of the diode arrow, which is how a Zener normally operates. This is going to be your reference current direction. And then this is going to be your reference polarity. So baliktad sa normal diode. No. How do I know whether this is in breakdown? I take the diode out, tanggalin ko siya sa terminals niya, I measure the open circuit voltage. When that is greater than 5 volts, then my diode will be in breakdown and equivalent to a 5-volt source. So I can show that here. No? So let's say this is 5 volts. Whenever my Vin is greater than 5 volts, my output will be 5 volts. Okay, when will it be in forward conducting mode? It will be in forward conducting mode now when my input is negative. Because only when my input is negative will the anode be positive with respect to the cathode. Kailangan itong Vin negative para ito maging positive with respect to this. And when the open circuit voltage is less than, because we're talking about the negative, no? We're talking about the negative voltage. It's less than minus V of F. That is when this will be conducting and its value will be negative V of F. No? So if we take a look at that, since it's silicon, that's 0.7, negative, the value will be negative 0.7 here. Then everywhere else, the diode is an open circuit and V out is equal to V in. So this is going to be my output. Okay, I'll stop there. There's another example given in the notes, but I think that one you can study on your own. I just wanted to introduce the Zener diode very quickly to you because it might be the first time you encounter the Zener diode. Okay. So that's all I have for this afternoon. I'll stick around for any questions, but other than that, if you're busy or you have something to do, then you can already leave the session. Okay, are there any questions? Okay, I'll close the session when the last person leaves so that kung may mga pahabol na may magtatanong, I'm still around.
Thank you, sir.
You're welcome.
sir.
Thank you, sir.
Thank you po.
Thank you,
Thank you
sir.
po, sir.
Thank you,
Okay.
sir.
Thank you, sir.
Okay, you're welcome.
Thank you po, sir.